In the last video we learned that a matrix is invertible if and only if there is a sequence of row operations taking it to the identity matrix. But how can we actually calculate the inverse of a matrix we know to be invertible? Well, let's suppose we have a matrix A which is invertible. Well, then there exists a matrix B such that, in particular, A times B is the identity matrix. And we'd like to find this matrix B. Well, let's introduce some notation for the columns of B. We'll call the columns of B C1, C2, and so on, up to Cn. So let's say A and B are n by n. So what we can say about B is that AB is equal to the identity, using the column-wise property of multiplication, A times B is the matrix whose first column is AC1 and whose second column is AC2, and so on. So that is true if and only if AC1 is equal to the first column of the identity matrix, and AC2 is equal to the second column of the identity matrix, and so on. That means finding a matrix B such that A times B is equal to the identity is equivalent to solving a bunch of matrix equations. So finding a solution to the matrix equation AX equals 1, 0, 0, 0, 0, and so on, and finding a solution to the matrix equation AX equals 0, 1, 0, 0, 0, 0, 0, and so on. That means we can solve our problem of finding inverse matrices for invertible matrices by using what we know about solving systems of linear equations. Before we go into the details of this, let's look why it's so desirable to find a straightforward and easy method for computing inverses. You've already seen the formula for a 2 by 2 inverse matrix. So there was a formula which said that matrix ABCD was invertible if and only if AD minus BC was non-zero, and if it was invertible then the inverse was 1 over AD minus BCD minus B minus CA. So you might think, oh well, there's an easy generalization of this, maybe there's some kind of nice generalization. Well, unfortunately there is a generalization, but it's not nice. Here it is. If you've got a 3 by 3 invertible matrix whose ij entry is A subscript ij, then this thing is invertible if and only if the expression delta, which I've written at the bottom here, is non-zero, and in that case its inverse is given by this formula, where the expression with 2 vertical lines means ADBC, like a 2 by 2 determinant. So I think you agree this formula is pretty awful. We don't want to use it in real life, and we really need a better way of computing general inverses. So here is the method we can use following the ideas that I wrote on the very first slide. To find the inverse if it exists of a square matrix A, in other words, to determine whether a matrix A is invertible, and if so, to find its inverse, you can do the following things. So first of all, form what I'm going to call a super augmented matrix. So normally an augmented matrix just results from adding one column to the end of A, but in fact we're going to add n columns to the end of an n by n matrix A. And that super augmented matrix is obtained by putting the identity matrix next to A. So if A was a 2 by 2 matrix, 1, 2, 3, 4, then its super augmented matrix will be 1, 2, 3, 4, and then the 2 by 2 identity. The reason this is relevant is because we saw that finding the inverse was equivalent to solving a whole bunch of matrix equations, which we would normally do with an ordinary augmented matrix, but instead of doing n different solutions to n different matrix equations, we can just do them all at once by forming the super augmented matrix, where each of the right-hand sides of the equations we're trying to solve is its own column in our super augmented matrix. The next step is to do row operations to put this super augmented matrix into row reduced echelon form, and then you can read off your solution. If you get the identity and then a matrix B, then A is invertible with inverse B. On the other hand, if the first part of the matrix, so the first n columns, is not the identity, then the row reduced echelon form of A is not the identity, so A is not invertible. So this procedure, to reiterate, both tells us whether or not a matrix is invertible, and, if it is invertible, determines its inverse. Let's do an example, in fact the example that I just showed you. So we will take A to be the 2 by 2 matrix 1, 2, 3, 4. Then to determine whether or not A is invertible, and if so, what its inverse is, we can start by putting the super augmented matrix A followed by the 2 by 2 identity into row reduced echelon form. So here is our super augmented matrix. We want to put this in row reduced echelon form. So we look at the top row, it's got a leading entry which is 1, that's fine, so we need to eliminate the other non-zero entries in its column, which we can do by subtracting 3 times row 1 from row 2. On doing this, the first column now has a leading entry 1 and every other entry 0. So we can move on to the next row. The leading entry in row 2 is not 1, so we need to change the leading entry so that it's 1 by multiplying by minus a half. On doing that, the leading entry in row 2 is now equal to 1, but there is a non-zero entry in the same column as the leading entry in row 2. We need to eliminate that, which we can do by subtracting 2 times row 2 from row 1. Now we found a row reduced echelon form matrix. This matrix is in row reduced echelon form. The first half of it, so this half here, is the identity matrix, therefore A was invertible, and its inverse is the matrix making up the second half of the row reduced echelon form of our super augmented matrix. So it's minus 2, 1, 3 halves, minus 1 half. And you can check both that really is the inverse of A by just multiplying it by A and seeing if you get the identity. You can also check that it's the same thing that you would have got by using the 2 by 2 matrix inverse formula. But the advantage of this method is you can use it for absolutely any square matrix of any size, and it's much more practical than using, for example, the awful 3 by 3 formula or an even worse 4 by 4 formula that you saw on slide 3.